Well, good evening, everyone. Thanks for the introduction, but just to correct that, yeah, without ground stations, it will actually be sci-fi. We need the ground stations to get the data down. Uh, so yeah, like I think since morning, we have a lot of sessions which took us through the journey of LLMs, or even there was one session on computer vision as well. I think there's one session after this on computer vision. Now, I want to take or gather the attention on how do we now take the AI and ML, the advancements that is happening here on Earth, like for terrestrial applications, up into space, like literally into space on satellites, right? And specifically, I'll be focusing on the edge computing, how edge computing will be able to, say, accelerate the data delivery as well as the decision delivery, okay? So I think everyone would have seen a satellite image on your phones or on your laptops, on Google Earth or Google Maps, right? I mean, can anyone say, like, what's so unique about this picture? Like, I mean, there is a reason why I have used this picture here. Well, like, I'll just go ahead. This is where we are currently. I'm pretty sure, like, a lot of folks who are coming here today would have used your phones to figure out, okay, like, how long will it take to get here? What's the best route to get here, right? And you have reached here because of a combination of a lot of different technologies behind that, right? One of them is satellite imagery. So if you open any satellite imagery on Google Earth and you keep zooming in, you'll start seeing, like on the bottom of Google Earth, you'll see like when was the picture taken and who was that satellite provider, right? And most of the urban areas like Bangalore, like we always have the most updated pictures. Like, so if you open today, it would show like, okay, by Maxar or Airbus at 2025, okay? And if you go somewhere like Thar Desert in Rajasthan, the last picture there would have been taken somewhere in 2024 or even 23, right? So while satellite imagery has been playing one of the key role in building base maps or mapping the world, there are a lot of other applications that we use satellite imagery. One of the important applications is to monitor the climate change, right? If we want to monitor global events at a scale, and we want to have a time history of how our Earth is changing, then satellite imagery is one of the best solutions out there. Then comes the disaster management. Like one of the most, I would say, spoken disaster, more recent was the wildfires in the west of the US, right? Where satellite imagery was used to understand how the fires were spreading, which way the plume is blowing, like what's the impact downstream, where the rescue operations should be planned, etc. Then comes the natural resource management. I think there was one article, I forgot the source, about Bangalore, like how the lakes around Bangalore have been drying up since like more than 25, 30 years, and there was a time lapse for that. And that time lapse was a composition of satellite imagery, and that is how you use data from satellites for natural resource management. Similarly, you have applications in the areas of forestry, land use, land cover mapping, and of course, the very well-known, the defense and security, right? And this small animation shows like how actually the images are collected from the satellite, right? So it has like a limited field of view. Satellites go around the Earth depending upon the well-known physics laws of either Newton, Kepler's, or other laws. So there are certain limitations, constraints with which we work around with. But if you want to monitor anything on Earth, anywhere, anytime, and at scale, then satellite imagery is one of the best solutions. Otherwise, then you have like other sources, like it can be like aerial imagery or even imagery from drones, right? So let me take you through the journey of data, like how the data reaches to your phone on Google Earth, right? So you are the end user, like we are all the end users where we use the data from satellites. But there is someone sitting there who is actually telling, okay, like I need to plan to collect data over a particular region, right? So that particular user, like we call that person as a user persona, that person puts up a request to the particular, say, satellite operator saying that, hey, I want to image over Kormangala area, like after 2 days, Like, can you do that, right? And that request goes to the satellite operator. The operator does like a feasibility study to check, okay, whether my satellite, will it actually pass over this area after 2 days? And if it does, then it goes to the operations team, where they say they transfer the command to the ground station, right? And the satellite has to actually come over the ground station, where then you uplink the command to the satellite saying that, okay, the command is uplinked to take the image whenever it goes over the area of interest, right? Then the satellite actually comes over the area of interest, it takes the images, but then again, the satellite has to wait to come into the view of the ground station to get the data down, right? That is the downlink, and then the data comes through the ground station, back to the satellite operator, and finally to the end user. Traditionally, this whole journey takes in the order of, I would say, 24 hours, and it can go all the way up to, like, say, 3 or 4 days, depending upon your propensity to pay the satellite operator, because everyone have their own, I would say, bandwidth, as well as their own anchor customers, so they would prioritize them, right? So how do we minimize this time to delivery, right? I mean, that is always a challenge. And here at KaleidEO, like, where we are focusing on the top two segments of this industry, which is the upstream and the midstream, where we are focusing building camera systems as well as the software systems around that to deliver the high quality data. And SatSure is a parent company which is focusing more on the end solutions, like how do we derive applications using the data from satellites, right? So like I mentioned, the bottleneck here is the visibility to the ground stations and the data rates at which we can get the data, right? I don't know, like, if there's a book that was circulated by the organizer, which is the yearbook for year in AI, right? And if you scroll to the 200th page, there is a chapter about why India has one of the ground stations in Antarctica, right? So depending upon your position of the ground station around the Earth, the contact time for a satellite varies. Like, how long can I see? Like, so if the satellite is going on top of your head, like, so it rises and it sets depending upon its orbit and where you are located. And typically this time range, if you're in Bangalore, can be in the order of, say, 4 minutes to 8 minutes, somewhere in that range, okay? And with the current radio system or the RF downlink systems, you have the ability to downlink at 100 to 400 megabit per second. There are some companies who are now going all the way up to, say, 700, 800 Mbps as well. So you have a limit at which you can, I would say, like, what's the volume of data actually you can downlink within a given amount of time, right? And traditionally, believe it or not, like, while we all might think that, oh, satellite industry or rockets is hi-fi, like, I mean, people are really intelligent out there, we still downlink images and figure out that, oh, like, in this image, like, maybe 30% of it was covered with cloud. It is not usable anymore, right? And this was the trend till at least 2018 or 2019, right? And that is where we started thinking, as an industry, started thinking about processing data on the edge. Okay, like, where the edge processing will help us in taking swift decisions in the matters of disaster. Like, one particular disaster where we have highlighted here was the flood that happened in Andhra Pradesh in the late August, early September of last year. So there, as a company, we actually processed the data to identify which was those critical areas where the inundation was more, the flood inundation was more than the next severe zone, or, like, we rated the, I would say, severity based on the event. And then passed on this information to the drone company so that they can plan their rescue or relief operations in a more systematic way, like delivering food, etc., to more affected regions and then go to the next regions. But this took us 3 to 4 days, actually. Like, I mean, the event happened, it was only 3 to 4 days, then we were able to give this information to our partner drone company, right? If we had the edge, like, if we were able to process the data on the satellite, extract the insight saying only tell me the region where the flood inundation is happening, which are the regions which were severely affected, And if you're able to go to them as soon as possible, it would have been very much helpful, right? And that's the whole, I would say, motivation for us to now process the data on the satellites. But you may ask, like, why have we not done this before? Like, I mean, edge is not a new concept when you talk about IoT or any applications here on the ground. Because on satellites, we deal with a lot of different constraints, right? Like, we cannot pop in another H100 card whenever we want. We cannot have like a EBS storage that we have the luxury on the cloud, right? Where we pull in extra storage whenever we want. Like, there is a fixed amount of resource on the satellite with which we have to work with. There are constraints on the thermal systems, like if the edge processor is continuously burning or like working, then it produces a lot of heat. Like, where do you throw that heat? So we work with that. And traditionally, satellite industry has been conservative because you build the satellite, which is quite expensive, and once you put out in the space, it's there, right? I mean, you can't go and repair it. You can't go and change things out there, which is why like people always test electronics like to the extreme environments before putting out there. But with the advent of, I would say, new space industry, like where the cost of satellites, miniaturization of electronics, etc., people are now taking risks. So one of the first GPU was put in space somewhere around 2019, right? And where they detected clouds and using a segmentation model and got the data down and rejected, like, say, whatever unusable data, right? So when we have processing capabilities on the satellite, we are able to reduce the volume of data that we will be downlinking. That means direct impact on the cost, that we'll be able to reduce the cost, as well as improve the turnaround time, starting from the client request to the analytics delivered to the end user, right? So typically, a system of edge, like, I mean, this is, I don't think there is anything new when differentiating between the terrestrial edge-based processing to a satellite-based edge processing in this model, what you see here. So you have an edge-based AI hardware. It can be a combination of your GPUs or VPUs or even CPUs. And on top of which you have the base software layer and operating system. And on top of that operating system, we deploy initial pre-processing data set. It can be involving starting from stabilization, calibration, then pre-processing, tiling, because you have like satellite image tiles, like where we need to further split it down. Then other utility applications, it can be cloud, sea detection, and then other utility apps. So essentially, whatever you capture the data from the sensor, you process the data close to the sensor just after collecting it and extract the insights so that you downlink only the insights from the satellite. So while we started building our own models, one of the first things that we realized was, okay, the actual time-consuming or process-intensive, like I would say, part of the whole chain was not the actual detection of clouds or buildings or any features that I want to detect. It was tiling the satellite image itself. So any satellite image, it can be in the order of, I would say, 260 or 500 megapixels, right? And each pixel will have multiple bands. We are talking about multispectral data, which has red, green, blue, near infrared. It can even include, say, red edge or like multitude of other bands depending upon the sensor. And when you have more granularity, that is more resolution with more number of bands, that increases the complexity. And hence, we have to tile the satellite image before we even do further processes, okay? And I mean, our engineers started with experimentation of executing it in serial manner on a cloud-based GPU, which was taking a long time. And then finally, we found that, okay, like, let's go with a combination of Numba plus parallel computing. Numba is basically your conversion of Python code into a more like a machine-level code, which is like a just-in-time compiler. And combine that with parallel threading, we get the most, I would say, optimized time out there. That is what we tested and again confirmed with our own edge development kit. saying that the NUMBA plus parallel computing method works the best. Then comes the raster operations, right? And even in the raster operations, we were able to optimize the iterations like 5 times faster than a traditional CPU that we usually use. Okay. So as a highlight, yeah, like I mean, we were able to optimize the CPU plus GPU inferencing 25 times faster. Then we built an automated, say, georeferencing registration code, like, which is basically assigning each pixel to a lat long here on the ground. Okay? And then we had one of the fastest tiling algorithm, which we think is faster than the open source GDAL like library out there. We built a GPU-based raster calculation kernel, then the heterogeneous CUDA grid innovation, and combination of these helped us optimize our algorithm to deploy on the edge. Okay? And we tested various different applications before even putting up our application into orbit. So imagine a use case where the user is interested to understand what are the number of buildings even in a given area of interest, right? The user is not interested in the shape of the building or the texture of the building, etc. So if that is the use case, then why not just build a model which will detect the number of buildings, and we get down the data saying that, okay, in a given area, like we have these many number of buildings, right? And building, preparing this model was, I would say, challenging, specifically through the Indian geographical scenario, because your training data set has to be as strong as the model inferencing. And on the edge, on satellites, we don't do any training. Like, we are just inferring on the satellites, where we build the model, we deploy the model on the satellites. Here on building, like, okay, there are different roof type cases. Sometimes in the villages, you might find someone is drying red chilies on the entire rooftop, right? I mean, that would be difficult to even detect sometimes by your model if that training data is not available. But we were able to get some good number out here. Then the next use case that we thought about was delineating or getting the road networks out from a given area. Like, I mean, this is very much useful in the case of disaster case of earthquakes, where you want to understand quickly which roads are still usable, like where there is a break between the roads, right? And this was, again, I would say segmentation-based, I think, unit model, and where we optimized. And this is the model that we finally deployed on the edge on a partner satellite. So a satellite which was already hosting a GPU-based computing platform. So we uplinked our model onto the satellite to test, okay, how does the model actually perform in a very resource-constrained environment, right? And here, the compute system was NVIDIA Jetson-based GPU. And the satellite was come by a satellite operator called Satellogic, where the image was somewhere between 0.7 to 0.8 meter resolution. Like I mentioned, this model was a unit-based road network algorithm where we delineated the roads. And this is the most interesting part, like how we were able to reduce the volume of the data. So this satellite scene, I mean, in fact, this scene, what you see here, the width of this scene is like around 5.3 kilometer, and the length of the scene is around 32 kilometers, if I am correct. So the original raw data volume of this scene was around 950 MB or so, okay, megabytes. And once we extracted only the road features, and that came down to 6 megabytes. So imagine, like, we are able to get down the volume by more than 90 or 95% here for different use cases. And the amount of time, the volume of cost that you will be saving, starting through the whole journey of getting the data from satellites to the end user, right? That is the whole value proposition of edge processing on the satellites. And here we were able to execute it, I would say, in a decent timeline of 1.5 minutes. But we should really, I mean, as an industry, I think we should really get it down to like less than 30, 40 seconds. Like, that would be the ideal target. Okay. Well, when we talk about the future of edge AI in space tech, like even though we process the data on the edge and reduce the volume of data, like yes, there is some improvement in the, I would say, TAT to the end customer, we are still limited by the time that we take to get to the ground station, right? I mean, currently that is the only way where we can get the data down, right? So in the future, like we are now seeing the rise of inter-satellite laser links, okay? So you have satellites talking to each other over laser comms and send the data across so that if the other satellite is, I would say, in the visibility of the ground station, you can transfer the data from that satellite to other satellite and get the data down even faster, right? And that comes under the enhanced autonomy as well as the inter-satellite comms. Then you have the evolution of the hardware and the miniaturization. Like we are now seeing with the advancement of semiconductor industry, how we are able to progress further in miniaturizing the electronics and ruggedizing those electronics, making it more reliable to put it on satellites. Then with the advancement in the analytics capabilities here on Earth, be it in the use of machine learning, the different open source models that we are now coming across, so how do we leverage that and put it up on the satellites, right? Further, like the scalable constellation development, like how do we deploy rapid, cost-effective satellite constellations where they have enhanced autonomy and constellation management. Say, if one satellite fails to take an image, it should automatically give a command to the another satellite saying that, hey, like, I mean, I was not able to take an image over this area. Can you take that in the next upcoming pass of yours, right? That onboard autonomous decision making is something that we are now looking forward into the satellite operations or operations and management. So here at KaleidEO, like while Edge AI is one part of the system, we are developing our own camera systems to put on satellites. We are developing two variants of the camera systems, which call them as the payloads. One is a high-resolution payload, which will be imaging in 0.7 or less than 0.7 meter resolution. The other one is will be imaging at around 1.2 to 1.5 meter resolution with a very wide swath. And we have tested a prototype of this camera system on an aircraft, and which helped us prove, okay, like whatever images that we are developing has one of the best qualities out there. And we are now working the data that we have collected. We have collected almost around 900 GB to 1 terabyte of data. We are now using this data to develop the models to be deployed on the edge. Well, thank you. That's about it. These are the actual images that we see from the camera system that we have captured. Yeah. Thank you.
Check. I am 100% sure there will be questions. Yes, let's get a mic to sir there. Then sir, then blue shirt sir behind. Black jacket sir here.
Should I be worried?
You finished your session way too early, but that's
okay.
A good thing because there are loads of questions. Let's get mics to them quickly. Yeah, that's okay, sir. We'll start with you, then we'll come to you. Let's get one mic here. Let's get one mic here to sir. From open text. Yeah, sir, you can start. Your mic is working.
Hello, yeah. Hey, nice, Akash. Very different session, I must say, because from the morning I'm listening agents and LLMs and all that. I'm actually hearing something different, so it's very refreshing. So the question here is two questions. You mentioned about H100s and all those things. Do we really need those things? Because the old robust ML model like YOLO and all those things, object detections, those all things are there from almost a decade now, and you can do that in edge computing there itself and get the filtered image down at the downlink. So we really don't need those kind of hardwares there, right? So so now you're saying that we don't have those stuff. What is your take on that? Because that pieces is already there in Atlanta glaciers. Also, people are doing that. So what's on that? Second interesting question, maybe once you answer the first one, is on the real issues that you are in Bangalore, right? So you have the images of satellites and all that. So must be thinking about the issues like the traffic management systems and the flooding systems and all the Rajkalva systems and all those things. I think this is one of the area where you can straight away work with the CM and then try to look into those kind of real issues, the social issues, because people are taking 2 hours every day, one-sided, by the way, right? If I'm not wrong. So those are the areas where I think you should really step in, and then this is the area where I think everybody is looking forward.
Right. No, thanks for the questions. So answering your first question, the H100 thing was just as an example. Like, of course, like we don't need such a heavy-duty system on the satellites. In fact, I think the industry is realizing that GPUs are not one of the best solutions for satellites because they are power hungry, right? And they emit a lot of heat. So we cannot have the luxury of building a cooling system on the satellite just because our GPU is throwing away a lot of heat. So this is the classic example of resource constrained, I would say, model development. I mean, so recently when the DeepSeek thing came up and it made waves, I was like, okay, I was happy that, okay, someone is talking about resource constrained models. And here on satellites, we are extremely constrained with resources, which is why now the industry is moving more towards FPGA-based processing system. But when we talk about FPGA processing system, the current ML models or deep learning neural networks, I mean, at least from my understanding, we do not have that setup like where you can directly deploy it on FPGAs. So there are some challenges in implementing those models on the FPGAs. So it's a trade-off. As an industry, like I would say satellite industry, we are still like say 5 to 6 years behind than the traditional LLM or even perception-based ML models that are available here in the industry. But yes, like we are moving more towards FPGAs than GPUs or H100s, something like that. Coming to your second question, yes, we are in talks with Government of Karnataka, but more towards monitoring the forestry and agroforestry use cases. Unfortunately, not towards traffic yet.
AI has kind of given up in front of Bangalore traffic. I'm just kidding.
So when you talk about urban use cases like monitoring traffic or monitoring buildings, you need very high resolution Earth observation data, right? And unfortunately, with the dearth of high resolution data available out there, the cost of the data is really huge, okay? So unless someone is actually ready to pay for it to, like, say, analyze, process, get the data as well, then yes, we can look into that. But currently, we are working with the government, and one is on the water stack implementation with the government of Karnataka, as well as the agri and agroforestry stack is what we are working.
Great work there, Akash. Sir, can we have your question?
Mr. Akash, I'm Sashikumar here. It's a good, it's a wide, scintillating and agile session. It's a totally, you have taken all of us into the space, and from there you thrown us to see how the earth is looking. It's a good thing. But because of having a lot of constraints and other things in the satellite imagery and the satellite getting links, can't we use the technology of high altitude flown drones with high image resolutions? As and when the situation demands, we will deploy the equipment and we get the things and to the ground, and we can process it, and we can deploy our resources to mitigate the natural disaster or climate. So in this, are there any technologies are available currently, or any work is going on?
So, like I mentioned earlier, it depends upon the application or the use case that you are looking to solve, okay? So if you're looking to solve something on a global scale, and where you want to monitor on a more regular basis, then satellites are one of the best solutions out there. But if you're looking for something like one time in a very small area or like a limited area, maybe it can be like a state. I mean, when I say small, it is the area as big as, like, say, Karnataka. Then yes, like maybe drones or a high altitude platforms, which we call as HAPS, are more suitable. In fact, like Government of India did the program of Swamitwa program, where they imaged the entire, I would say, more than 700 or 800 villages. No, not villages, I think districts, and using drones, and they are now mapping out the actual houses, like how the houses are built and what are the number of houses, etc. We are a part of that program in analyzing the data as well over there. So I would say when you talk about different spectrums like drones to aircrafts to high altitude platforms to satellites, there are different types of problems for which different things are more suitable. So the cost and the unit economics also will be different for different things.
Next question.
Yeah, hi Akash. So this is Soumya Anand from Caterpillar. So I want to just say that this is the first session that I marked when I got the agenda. So
Glad
I'm
to
really
know.
happy that I love the session. I have a very small question. I'm good with the hardware component, what you have explained, but let's say if you want to change the models, AI models which are deployed in edge, right? Let's say you have said some predeterministic models like sea and ocean detection, and you will have one for land detection, one for house detection. Have you faced a challenge, something like you want to change the model on the fly? So is it something that you're working, or is there a challenge at present if you want to change the model on fly?
Yeah. I mean, there is definitely a challenge. Okay, we haven't faced that challenge because we have not deployed the solution on a day-to-day basis or on scale yet. The whatever test that we did on the satellite in 2023, that was like a one-time demonstration thing. So whenever like we have our own satellites, we will be implementing this as well. And we have thought about this challenge. Like we definitely know that once we deploy the model, sometimes it might work. And if we want to push some software updates or patch update to it, like we have to update it. So the traditional way is you go ahead and you put a patch update through a command whenever the satellite is passing over the ground station. But there are, I think there are some non-traditional ways which we can explore where the model keeps learning on top of it. But that again implies some compute resource utilization on the satellite. So there is a trade-off out there. Other ways, we can deploy multiple models up there. And once we understand which model is working, okay, like we can reject the models which is not working.
Hi Akash, I just have one question here at the back.
Okay.
So my simple question is, why are we so obsessed about having the compute on edge? Why not just keep it on cloud so that we can experiment with the models more and so on? So what's the major advantage?
So I think there is one thing, like say cloud detection, that has to be done on the edge. I mean, there is no question about it if you ask me, right? What is the use in getting a scene of say 10 kilometer by 15 kilometer satellite image from the satellite delivered to you, passing through the entire chain of ground station operators, like there is entire operations cost involved there, and finally you realize that 70% of this scene is cloud, this is not usable to me, but you end up paying for it because you have actually requested for that image, right? So there definitely you need it. But when it comes to other applications of, okay, do I need to detect buildings? Do I need to detect trees? Or do I need to detect even cars? Like there were actually companies who were detecting cars, but after downlinking. There, it is a matter of business case. Like, is the end use very clear? Because once you process the data on the edge and reject the pixels, that data is gone, right? I mean, you don't get that data back again. So if your end use and the business case is very clear, then yes, you can go ahead and do pursue this mode of edge computing. If not, then just leave out the area which is not interest to you, where you are very sure, okay, I don't need the clouds, I don't need the sea. Like if I'm imaging a coastal area like Mangalore, where I want to understand how the port or what's the progress in certain construction near the port, then I will just reject the pixels which have C, right? I mean, I'm not interested in that. So that is the way forward, in my opinion.
All right, let's have the question from Sir here. We'll try to keep the questions a little short. We have time for just two more.
Can you hear me? Yeah. So very good session. So really enjoyed it. So I work as an AI architect building autonomous networks. So I have two questions, very short ones. So one would be data privacy. So you said you just do inferencing on the edge. You cannot train, obvious reasons. So how do you handle that? Because you cannot deploy one model which is trained on somebody's images. You cannot use that for somebody else. So how are you handling that? Another one was the latency. You said it takes 1 to 3 minutes for you to just get that data downlink or whatever. And then to pass, say, an area, it takes 8 minutes. So you would have lost images by then. So what is latency against what are you calculating? So is there any metric where you measure that?
Right.
So that
Now, I'll take a first question. Of course, like the diversity of training data really helps in building a robust model. So whatever data that we are training, we ensure that, okay, like we are taking some data from India, like where the buildings are like slightly more haphazard than more traditional, like say in the US or somewhere where things are very much planned. So diversity of data definitely matters. If you don't have the data diverse, then the model fails, okay? Then coming to your second question regarding latency, well, the metrics, if we are able to downlink the data, like you can imagine if we are compressing the data from 900 megabytes to say around 2 megabytes, at 400 megabits per second, you can actually do the math, how much time we can come back, like, I mean, we can get there. So that's the amount of data or like time that we save in getting the data down and the latency in transmission. But the latency in delivering the data after downlinking still remains the same. So that is still there. That challenge is still there. But that is where now we are innovating, okay, like whatever we are deploying on the edge, the same model now we are deploying on the cloud. So even our cloud utilization costs are coming down because of the development of edge-based processing systems. So yeah.
Akash, before we let you go, I have one last question that I would like to ask you, and then, sir, a short one. Quickly, I'll ask you, around 6 to 7 months back, during the Indian National Space Day, I was shooting 2 back-to-back podcasts, one with Dr. S. Somnath, sir, the ISRO chief, and the next one with, I'm sure you might know him or the organization for sure, the founder of Skyroot Aerospace, Naga Bharat Dhaka. Exactly. Somnath sir was telling me that with NASA, with ISRO and the private sector playing hand in hand, coming in together, the prospect of Indian space travel is mammoth in the coming years. And Naga said the same, that in not very far away in the future, there will literally be possible where humans will be able to do space travel. And that's not way too far ahead in the future. Can you tell me how much of a role can generative AI play behind this, and how will it make it happen even quicker?
Well, you put me in a spot there. Well, people do travel to space even now. So there are people now, right now, living up there in the orbit, either in International Space Station or even in the space station by China. So there are people living up there. What Somnath sir or others are speaking is, how do we send humans from India? Right?
Civilians, they meant.
Civilians,
Yeah.
civilians from India. In fact, one civilian is flying on the private space system, that is the Axiom space. He is scheduled to go in the next few weeks. An Indian planning to go in the next few weeks.
And that person is not an astronaut or a space scientist?
No, he's an Air Force pilot from Indian Air Force, so he's planning to go there. I mean, the question is, how does generative AI, like how can we accelerate using generative AI?
Exactly.
Right? When you talk about human space missions, reliability and fault tolerance becomes one of the most important, I would say, aspect. No, like critical system can fall. Like if it falls, like, I mean, there is a risk to life out there. So people in ISRO are now working on AI-based fault tolerance models, where you can actually detect an anomaly on the either a spacecraft system or a launch vehicle system even before the anomaly can occur, and try to fix that, or like take a decision how to fix that anomaly. That is one thing on top of my mind. But yeah, sorry, like I can't think of anything else. But this definitely, I think, is where there's a clear use case of generative AI for space systems out there. Yeah.
Thank you so much, Akash. One last question, because I promised you, bro. We'll keep it short.
Yeah, I will make it quick. Nice presentation, Akash. So my question is, you said we came to this level of sending GPUs to the edge. So how far away we are from using zero-shot detection or open vocabulary models in the edge itself? To with like Sar also asked, like you said you have lack of training data when crafting solutions for traffic and stuff, because you don't have data. But these open vocabulary models and zero shot detection, you don't need data per se. You just send a prompt like Florence to grounding Dino or Sam, even Sam. So how far away from us to upgrade to that level so that we have those models in the edge to process that?
I mean, like if personally, I think like maybe another 3 to 5 years is what my expectation is, because there are some companies who are now working towards setting up data centers out there in space as well, like who are thinking of setting large data centers. It can be like storing of data, processing of data, and relaying the data. So there are some companies. So when they do that, like let's see like if this happens out there.
Yeah, fingers crossed.
Ladies and gentlemen, I'm not wrong here to say that that was one of the sessions that got the maximum amount of engagement. Can we have a huge round of applause here for Akash?
Thanks everyone. Thank you.
Thank you so much, Akash.
Yeah, thank you.
Some really path-breaking work that you guys are doing.